Welcome back to Prescribing Hope, Azithromycin Unmasked. I'm Rittika, your host with a master's in neuroscience, passionate about dissecting molecular intricacies of antibiotics. In today's lecture, we are going to address the mechanism of action, how azithromycin works as a macrolide. We are zooming deep into how azithromycin battles bacteria at a cellular level, a critical piece of the story before its entry into the unexpected COVID 19 role. With us is Saakshi, who has a master's in microbiology and she loves cracking the bacterial code. She is here to help us navigate azithromycin's tactical playbook, the cellular battlefield, where ribosomes are the front lines and chemistry is strategy. Welcome back.
Thanks, Rittika. I am thrilled to dive into azithromycin's molecular playbook. It's like decoding a master strategist's battle plan.
Let's jump right in. Azithromycin's a macrolide renowned for halting bacterial growth. Can you break down its precise mechanism of action on the bacterial ribosomes, including the specific site and molecular interaction, and clarify whether it's always bacteriostatic or sometimes bactericidal?
Absolutely, Rittika. Azithromycin targets the 50S subunit of the bacterial ribosome, a molecular machine that translates mRNA into proteins. Specifically, it binds to the polypeptide exit tunnel near the peptidyl transferase center, interacting with the 23S rRNA at domain 5, particularly nucleotides A2058 and A2059 in E. coli. This binding blocks the tunnel where the growing peptide chain exits, hence halting the process of translocation. The step where the ribosome moves along the mRNA to add the next amino acid. By stalling this process, azithromycin prevents polypeptide elongation, effectively pausing bacterial protein synthesis. This action is primarily bacteriostatic, which means that it stops bacterial growth, hence allowing the immune system to clear the infection. However, at higher concentrations or against highly susceptible pathogens like Streptococcus pyogenes or Haemophilus influenza, it can be bactericidal, which means directly killing bacteria by disrupting critical protein production. The bactericidal effect depends on various factors such as drug concentration, bacterial species, and even growth phase. Azithromycin's polyketide structure, with its 15-membered azylide ring, ensures tight ribosomal binding, giving it a robust affinity compared to other macrolides like erythromycin.
Sakshi, you have described azithromycin's ribosomal assault like a cunning saboteur, jamming a factory's assembly line, halting production with precision. Its ability to toggle between pausing and destroying bacteria is like a warrior choosing between restraint and lethal force. Building on that, how does this ribosomal targeting translate to azithromycin's broad spectrum activity? What specific pathogen does it tackle and why is it so effective against atypical bacteria?
Great question, Rittika. Azithromycin's ribosomal target, the 50S subunit, is conserved across many bacteria, giving it broad spectrum activity. It's highly effective against gram-positive bacteria like Streptococcus pneumonia and Staphylococcus aureus, the non-MRSA strains, which cause pneumonia and skin infections as well. It also covers some gram-negative bacteria such as Haemophilus influenza and Moraxella catarrhalis, the key players in respiratory infections like otitis media, and bronchitis. It also covers some gram-negative bacteria such as Haemophilus influenza and Moraxella catarrhalis, which are the key players in respiratory infections like otitis media and bronchitis. Its standout strength lies with the typical bacteria, including Mycoplasma pneumonia, Chlamydia pneumonia, and Legionella pneumophila. These pathogens often lack a traditional cell wall, making them resistant to beta-lactams like penicillin. But Azithromycin's intracellular penetration and ribosomal action hit them hard. Its lipophilic nature allows it to accumulate in phagocytes, which ferry it to the infection sites, and its ability to penetrate host cells targets these intracellular bugs effectively. This makes azithromycin a go-to for community-acquired pneumonia where atypical pathogens are common, and for sexually transmitted infections like chlamydia, where a single dose can suffice. The broad coverage stems from its molecular versatility and pharmacokinetic edge, but it's not universal. Some gram-negative bacteria, like Pseudomonas aeruginosa, are naturally resistant due to efflux pumps or impermeable membranes.
Sakshi, you've painted azithromycin as a versatile archer, striking a wide array of bacterial targets with arrows tailored for both surface and hidden foes. Its knack for infiltrating cells to hunt atypical pathogens is like a spy slipping behind enemy lines. This ribosomal mechanism seems robust, but resistance is a growing concern. Can you dive into the molecular mechanisms of resistance and how they impact azithromycin's efficacy in clinical settings?
Resistance is indeed a critical challenge, Rittika. Bacteria evade azithromycin through three main mechanisms. The most prevalent is the target site modification, where the ERM gene encodes a methylase that methylates the 23S rRNA at 20 at A2058, altering the ribosomal binding site so azithromycin cannot latch on. This is common in Streptococcus pneumonia and Staphylococcus aureus, with resistance rates reaching 20 to 40% in some regions. Second, efflux pumps, encoded by genes like MEFA or MRS or MSRA, actively pump azithromycin out of the bacterial cell, reducing intracellular drug levels. This is seen in streptococci and some gram-negative bacteria too. Third, the rare enzymatic inactivation occurs via esterases or phosphotransferases that chemically modify azithromycin, though this is less common. In clinical practice, resistance reduces azithromycin's reliability, particularly for respiratory infections. For example, in area with high streptococcus pneumonia resistance, azithromycin may fail in severe pneumonia, promoting combination therapies or alternatives like fluoroquinolones. Overuse, especially in outpatient settings, has fueled resistance, underscoring the need for antimicrobial stewardship. Rapid diagnostics like PCR for resistance genes are increasingly vital to guide therapy and also preserve azithromycin's utility.
As if you have framed a resistance as a bacterial fortress raising shields, methylation pumps enzymes like a city bolting its gates against an invader. This arms race threatens azithromycin's region, demanding smarter strategies. In COVID 19, azithromycin's antibacterial mechanisms didn't directly apply to the viruses. Can you explain why its ribosomal action doesn't target viruses and what alternative effects sparked its exploration for COVID 19?
Exactly, Rittika. Viruses lack ribosomes, so azithromycin's 50S subunit blockade is irrelevant to them. They hijack host cells for protein synthesis. Its antibacterial mechanism targets bacterial pathogens and not viral replication. However, azithromycin's immunomodulatory effects observed in diseases like cystic fibrosis drove its COVID-19 interest. It reduces pro-inflammatory cytokines like IL-6 and IL-8, inhibits neutrophil influx, and also modulates pathway like NF-kappa B, NF-kappa B, creating an anti-inflammatory environment. In the early 2020, with COVID-19 cytokine storm linked to severe outcomes, azithromycin was tested to dampen this hyperinflammation, often paired with hydroxychloroquine. In vitro studies suggested weak antiviral activity by disrupting lysosomal function, but clinical trials like Recovery found no significant benefit in hospitalized patients. Its COVID-19 role leaned on immune modulation, not ribosomal action, though resistance risk tempered enthusiasm. We'll explore this further in the next lecture.
Sakshi of cast azithromycin as a bacterial specialist, turning reluctant diplomats powerless against viruses' aliens' machinery, but offering to calm the immune system's tempest. Its COVID pivot feels like a swordsman trying poetry in a new war. Thank you, Sakshi, for a molecular masterclass. I'm Rittika, and this is Prescribing Hope, Azithromycin Unmasked. Stay curious.